In a hypothetical fusion research laboratory, high-temperature helium gas is completely ionized, meaning that all the electrons are separated from the nucleus, and each helium atom is separated into two free electrons, and the remaining positively charged nucleus, which has two protons, which is called an alpha particle. An applied electric field causes the alpha particles to drift to the east at 25 meters per second, while the electrons drift in the other direction, the west, at 88 meters per second. The alpha particle density is this, 2.8010 times 10 to the 15th cubic centimeters. So we're going to have to convert that over to meters probably. What are the net current density and the current direction? Okay, so we can start with either the two protons or the electrons, doesn't matter. We're going to start with the alpha particle, the nucleus, and I'm going to say it's moving this way to the east. And I'm going to do a little 2e right below it, just to know that it has a charge of 2 electrons, because the helium atom started as neutral. You lose two electrons. Now its charge is going to be the same but opposite. Okay, so we want to find the net current density. So current density uses the symbol J, and what that means is it is a current, right, that is I, over an area. And so what I'm going to look at now is current, and the definition of current is, well, the unit for current is ampere. And an ampere is 1 coulomb per second. And what it means is you're counting how much charge is moving past a point, and you're going to use the units of coulomb to measure the charge, and you use seconds to measure the time. And this really isn't a hard problem, but it's easy to get confused if you don't understand what's going on. So that's why I like to kind of break it down. So here I'm going to say that this is x equals 0. This is a distance here. We know that the velocity of our alpha particles is going to be delta x, delta t. That's supposed to be an x. And that is going to equal 25 meters per second. 25 meters per second. So this is x equals 0, and I'm going to say that delta t equals 1 second. Well, what that means is that if this is x equals 25 meters, then since the particles are moving, the charged particles are moving at 25 meters per second over a period of 1 second, every particle that was within 25 meters, this distance right here, will have crossed over this imaginary line that we made here. Now, one thing to kind of keep in mind is that this really isn't a line per se, this is a plane. So we're actually looking at a volume. This whole volume, I'll do it this way. This whole volume is going to the right. And so after 1 second, this volume in here is going to move past our plane. And that's what we're concerned with for the current density. So the way we're going to think of this is the volume. So the volume of this right here is going to be delta x, which we called 25, multiplied by the area. I'll just call it A. Delta x times area, that's going to be the volume that moves past our imaginary plane right here. So I know it sounds complicated. We'll try and work through it, make it simpler. Okay. So now I'm going to start looking at the data that we have. So we're given alpha particle density. That alpha particle density, that's going to give us the charge density. So I'm going to do rho for density. I'm going to put a little C here, just so we, actually I'm going to put a little Q there for charge. Q is for charge, because whenever you see density, it usually means volumetric density, but you don't know if it's mass, charge, whatever. There's all these different types of densities. So put a little Q there for charge. And our density is 2.8 times 0.1 times 10 to the 15th. I'm going to write alpha here because these are alpha particles over centimeters cubed. And instead of writing centimeters cubed, I'm going to write centimeters multiplied by each other a total of 3 times. It's the same thing, but it keeps me more honest when I try to convert. All right, so now we got this. We want to convert this over to coulombs. So let's see, 1 alpha particle is 2 electron charges. So it's going to be 1.602 times 10 to the negative 19th. And that's going to be coulombs. The charge of an electron is negative 1.602 times 10 to the negative 19th coulombs. The positive version of that will be for the proton. A helium nucleus has 2 protons, therefore we multiplied by 2. And then for the centimeters, there's going to be 100 centimeters, which I'm going to write as 10 squared. 10 squared centimeters per meter. And I'm going to do that 3 times because we have centimeters cubed, and we want to get rid of all the centimeters and convert them all to meters to give us cubic meters. All right, so now we're going to do some canceling. Alphas cancel, the centimeters all cancel, and we are left with a charge density of, let me head over to Wolfram real quick. So Wolfram tells us, let's see here, we'll do 2.8801 times 10 to the 15th times 2 times 1.602 times 10 to the negative 19th times 10 squared, but we're going to do that 3 times, so it's going to be 10 to the 6th. And that should give us a number. That's actually a pretty big number. Did I do that right? Maybe. So let's see, that's 10 to the 6th. Yeah, that is. 10 to the 6th, that gives us 10 to the 21. Yeah, maybe. Might even, that's a lot of charge. So 897.4 coulombs per cubic meter. Okay? So the current density is going to be the charge that passes through this plane on the right side right here, so charge, over a given delta t. And we're going to divide by the area 2. And the reason we're dividing by the area is because we want to find the volume that passes through this area. And since the motion right here is perpendicular to the area, this area is going to be that area over on that side too. I know it sounds confusing. I apologize. So density is going to be, let's see here, charge per unit volume. Therefore, the charge, Q, is going to be the charge density times the volume. And this volume of this area is going to be delta X times the area. And so then when I plug this in down here, we get the charge the charge that passes through our plane for a given amount of time is going to be charge density times delta X times A, which is Q, this is the charge, times A delta T. Long story short, the A's cancel, and dx dt is the same as velocity. And so you will often see current density written as the charge density times velocity of the charges. And that's pretty much all it is for J, the current density. So I know it feels kind of like a long explanation just to get to something that's like, oh, it's just the formula, memorize just the formula. That's true. But current density feels unintuitive enough to me that I kind of want to have a deeper understanding and feeling about what it actually means. And I use it infrequently enough that I think it's worth having a base understanding of what's going on. That way you're less likely to get completely off track. All right, so now we have our formula. We're going to work with it. So the current density, the current density for the alpha particle is going to be the charge density, 897.4 times the velocity of the alpha. The current density of the electrons, Je, is going to be the same current density because the electrons literally come from the nucleus, which was initially neutral. So you basically have the positive, negative, split them off. By convention, positive current is positive charges moving in the positive direction. Well, in reality, it's the opposite of that, though. Electrons moving in the negative direction, and so we have negative charges moving in the negative direction. Either way, these both add up to the current in the same direction. A positive charge moving in the positive direction is the same as a negative charge moving in the negative direction. And so 897.4 coulombs per cubic meter times the velocity of the electrons. And so the total current density, these are going to reinforce each other. So we're going to have current density from alphas, current densities from the electrons, which is just going to be 897.4 coulombs per cubic meter times, and then we're going to have 25 plus 88. So we're going to have 25 plus 88. These are in meters per second. And when we cancel this, we get coulombs per second, which is current, amps, per square meter, which makes sense. It's kind of good to look at that from a dimensional analysis point of view, just to make sure we're not completely crazy. All right, so now we'll take our answer, and we'll do 25 plus 88 times 897.4, and we get a massive current. 1.01 times 10 to the 5 amps per square meter, which is a massive current density. Many amps. Yep. So to kind of backtrack what we did here, and what's the current direction? It's to the east. It's the same direction as the positive charges. So part B would be east. All right, backtrack what we did here, kind of summarize. To recap, what we had was we wanted to find the current density due to moving charges. And they give us literally the charges, which are alpha particles and electrons, and they give us a speed associated with them. And so what we did is we look at current density. Current density is the idea of current divided by area. And then current can be viewed as charges per second, so coulombs per second specifically. And so then we looked at the idea of like, all right, if we have delta x, we have this shape, the amount of volume that's going to move past this plane in a given period of time, delta t, et cetera, et cetera, et cetera. And we kind of justified to ourselves that, all right, the equation for current density, because it's a vector direction, is just going to be the charge density times velocity. And if you're wondering about the negative sign and why I justified adding them, the current density, even though I used the same current density for electrons, it's actually going to be negative. So what happens is, even though the velocity of the electrons is opposite direction, the current density is negative. Negative times negative gives you positive. So that's the mathematical justification about why that works. So really the hardest part was just converting our alpha particles to the equivalent coulombs that's moving. After we got that, we said it's the same as the electrons, and then plugged it in, and we got an answer. So hope that helped. See you on the next problem.